In the last segment, we looked at how to determine whether a bond was polar or not. And what we did was we used an electronegativity chart, took the difference, which means you subtract. Remember, it can be this number minus this number or this number minus this number. You take the absolute value. All differences are 0 or higher. And from there, you determine whether the bond was polar or not. But that doesn't necessarily mean that the molecule itself is polar. So I preloaded this sheet because I'm not going to lie, I've done it 3 times and my dogs keep barking. So I'm just going to use my notes and talk through them. We looked at easy ones before, I believe on page 11 and 12, the Hofbrinkels, of how they come together to make a Lewis structure that makes the octet achieved. Except for hydrogen. Hydrogen only gets 2. We saw that a single line was a single bond, 2 lines, 4 electrons, double bond, 3 lines, 6 electrons, triple bond. Now what happens when it becomes more challenging than just these simple ones here? Well, our process is going to be that we're going to count the valence electrons. So that means you need a periodic table available. Once you do that, you write a reasonable symmetrical structure. There should be a central atom that's obvious. Then you want to make your bonds. Okay? Assign remaining electrons to make sure the octet is achieved. So you're going to have a total here, you're going to bond, you're going to subtract those bonding electrons out, and with the remaining electrons, finish up your structure. Most are going to have 8, but there are some exceptions like hydrogen, which gets 2, and others that can have an expanded octet. Those are the ones that have electrons in n equals 3 or higher, because when you have n equals 3, you have a 3D shell available. Remember, when n equals 1 or n equals 2, there is no such thing as a 1D or a 2D, so you can't expand. Okay, then double or triple bond from there if you need to. Okay, now a couple of hints. If there's more than one carbon, link them together first. No lone pairs on carbon. You want to fill in carbon so it gets 8 electrons, no lone pairs. Have a little mantra: carbon is king, carbon is queen, carbon is royalty, carbon is this, carbon is that, whatever you want to say, but you have to make carbon happy first. Pretty much start there, link them together, no lone pairs. We'll be doing a ton of these on the lab sheet, which is valence shell electron pair repulsion, and we're going to do these lectures and the $1.98 tour and go back and forth between those tasks in this sheet. Okay, so CO2, you want to get out your periodic table. Carbon is in group 4, oxygen is in group 6, and you have 2 of them. So you have 16 valence electrons. Start with carbon, make it symmetrical. That means you put a carbon on each side, and then you make carbon happy with 4 lines or 8 electrons. That's how you get the 8 electrons that you subtract out. That gives you 8 electrons remaining, so the smart thing to do is to put 4 here and 4 here. 2, 4, 6, 8 on the oxygen, 2, 4, 6, 8 on the carbon, 2, 4, 6, 8 on the oxygen, so everybody has its octet. 2, 4, 6, 8, 10, 12, 14, 16, those are the 16 electrons that you began with, and so this is your Lewis structure of CO2. C2H6, carbon is in group 4 and there's 2 of them. Hydrogen is in group 1 and there's 6 of them. 8 plus 6 is 14. Start with carbon by linking them together. 6 hydrogens, the smart thing to do is divide that 3 and 3. Put 3 on this carbon, 3 on that carbon. Make sure carbon has 8. 2, 4, 6, 8. 2, 4, 6, 8. And now count up all your bonding electrons and subtract from 14. 2, 4, 6, 8, 10, 12, 14. Poof. No electrons. Everybody's happy. This is your Lewis structure. Next page, we move on to polyatomic ions. And here my dogs go again, so if they do, I'm going to yell at them to be quiet. 5 for the nitrogen, oxygen is in group 6, and there's 3 of them, and we have a negative charge, which means we add 1 electron. That gives us 24. Nitrogen is logical to be in the middle, 3 oxygens around. And what you find is that when you divide up the 18 remaining electrons, nitrogen doesn't have its octet, so you need to donate. And that's how we got this one here. We have a double bond right there. The fact of the matter is there's no law that says you have to donate these electrons. You can donate electrons here or electrons here. If you donate these electrons, you get the double bond here. If you do donate these electrons, you get the double bond there. So all 3 of these are valid Lewis structures for nitrate. And since you're moving electrons and not atoms, these are what we call resonance structures. So one of your jobs is going to be to find all the possible resonance structures in the lab handout that we're going to do together. Some structures have resonance, the other ones do not. There's no other valid way you can write these by moving electrons around. So these don't have any resonance structures. Some do, some don't, and we're going to find those together. Okay, ammonium ion. Nitrogen is 5, hydrogen is 1, and there's 4 of them, and we have a plus charge. Remember, to get a plus charge, that means you have to lose 1 electron. That means we have 8 electrons to work with. Nitrogen is the logical central atom. 4 hydrogens surround. Then we count bonding electrons. 2, 4, 6, 8. We have 0 remaining. So this is our Lewis structure for ammonium, which is covalently bonded, but the overall molecule has a plus charge. And this shows us how and why we get our polyatomic ions. We have to gain or lose electrons in order to get our valence octet. If we only had 23, this wouldn't work. If we had 9, this wouldn't work. Okay, so you're going to want to try this with the other polyatomic ions as practice. Okay? Okay, couple more, we'll wrap this up. C2H2, carbon is in group 4, there's 2 of them. Hydrogen is in group 1, and there's 4 of them. Again, you should have your periodic table handy, so this makes sense to you. 8 plus 4 means we have 12 electrons. Carbon is king. We're going to have 2 of them. They're going to link together. 4 hydrogens distributed symmetrically means we put 2 on each. Carbon here only has 6. Carbon here only has 6. No lone pairs on carbon, so we're going to double bond it. Let's count now. 2, 4, 6, 8, 10, 12. There are no electrons remaining. Everybody's happy in this structure, so this is our Lewis structure for C2H4. Now the last one, SF6, sulfur is 6, fluorine is 7, and there are 6 of them, so we have a total of 48. And the logical thing to put in the middle is sulfur with fluorine, 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 and then sulfur has 8, and so what students will do is they will try all kinds of renditions of trying to put fluorine on another fluorine. I can save everybody the headache and say that that will never work. And what you have to do is you have to put sulfur in the middle and 6 fluorines around it. You've used up now 2, 4, 6, 8, 10, 12, so 48 minus 12 is 36. 1, 2, 3, 4, 5, 6 fluorines, 36 electrons means the logical thing to do is to put 6 electrons on each. 1, 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. Yay! 36! And so now we've used up all of our electrons and the fluorines are all happy. And so you look at that sulfur and you say, now wait a minute, There's 2, 4, 6, 8, 10, 12 electrons on that sulfur. Well, sulfur is an example of an expanded octet because sulfur's highest N level is N equals 3, which means the electrons can expand, and therefore this is your expanded octet. Again, we'll see more of these on our VSEPR handout, and you will be advised to complete these as we go along on that sheet. There's about 6 pages of them, and by the time you're done, you will be a master.